Yeah. So good evening once again. So I am Sai Krishna. Welcome to week 6 of NPTEL program of electrical machines 1. So today we will be discussing a concept on transformers, which is a parallel operation of transformers. So we will just discuss the basics of parallel operation of transformers, and we will see what exactly is a parallel operation of transformers. And one second, excuse me. So what exactly is a parallel operation of transformers, and how do we connect two or more transformers in parallel, and what are the conditions for that parallel operation to satisfy, and what are the conditions to effectively operate any two transformers or two or more transformers in parallel operations. We will see those concepts today, and eventually we will solve a couple of problems on the said topic so that you will get understand what exactly this parallel transform operation is and how exactly does this works. So moving forward, again, today's topic is parallel operation of transformers. So let's say two or more transformers we want to connect in a parallel fashion. When it comes to parallel fashion, let me just draw here. Yeah. Let's say let's take first start with the two transformers. Let's start with the like basic two transformers. If we want to connect two different transformers in parallel, so we know that every transformer will have its own primary and secondary. I'm just drawing here first transformers primary, first transformers secondary, second transformers primary, and second transformers secondary. So this is basically primary, and this will be the secondary of a transformer 1, and this is transformer 2. Now let's say these two transformers, and we want to connect these two transformers in a parallel fashion. That is, these two primaries are connected. Okay, I'm just connecting these two primaries and these two secondaries, and this is a parallel fashion. The terminals will be connected together, and I am giving supply to my primary. Okay, and I am connecting a load between my secondary. So this is our transformer. Like we will excite one winding and we will connect a load at the second winding. So yeah, let's say supply, and this is any load. Now yeah, so naturally there are some conditions before connecting any two transformer. We can't just connect any transformer. One second, someone has joined. Yeah. So we can't just connect any two transformers randomly. The connection can't be any random. So there are certain conditions which should satisfy before we connect any two transformers in parallel. So the first condition, which is obvious, like anyone can uh, anyone can guess what should be the first condition before connecting any two transformers in parallel. When it comes to parallel, the terminal voltage of two systems should be same. Then only the parallel connection should be viable. Okay. Yeah, so we will see that. Let me just write it, the condition. Okay, now you see, we just saw the connection of these two transformers, and now we will see what are the conditions to satisfy before connecting any two transformers in parallel. The first condition, which is basic condition and very obvious condition, is the voltages of two transformers must be matching. So that means must be same. That's the first and foremost condition before connecting any two transformers. Like let's say, example, you have taken 400 volts and 200 volts, like x kVA. We don't really care about kVA right now, because kVA can be anything that's synonymous to current. So we are concentrating on voltage values here, and yeah, of course, we are looking at a single phase transformer, and in India it's a 50 hertz supply. Now you can't connect a transformer in parallel with this transformer if the other transformer rating is something like this, or 200 slash 500 volts. This kind of connection cannot be connected, because the voltage ratings, the LV side, HV side voltage rating should match. Then only you can actually connect a transformer. We will have to make sure about that before connecting any two transformers in parallel. The voltage rating should be matching. So before going into a rest of the conditions, and we have 3 or 4 more conditions to satisfy before connecting a transformer in parallel. But before going that, we will first think of the actual question. Like, we were discussing about parallel operations, but why it is required at all? So what is the need to connect any two transformers in parallel? So is it related to any application side, or what is the need? So we have two transformers. Why this idea of connecting two transformers in parallel came in the first place? So any idea why there is a need to connect any two transformers in parallel? So anything you think of, like any advantage of this parallel connection? Okay, I'm just giving an explanation here. Let's say we take a power system, that is entire power distribution network. We see, especially if we concentrate on the distribution side, like where the households get the power
We
from.
can increase the boost the voltages, and we can share the loading. Load sharing can be done.
That's exactly right. Load sharing is very important, because if we talk in load sharing, what exactly is load sharing and how this parallel operation can help? Boosting voltage may not be, because the voltage is really not boosted here. Like if we take an auto transformer or tap changing transformers, then we can talk about voltage boosting. Now parallel operation doesn't really talk about voltage boosting, because we ensure that voltage ratings are same. But the other point which you said, that load sharing, that is a very key parameter in parallel transformers. We will see that why it is important. So let's say we take the distribution level of power distribution in our households. Like, we are getting power from any nearby substation. So let's say the last transformer substation, where it will give 6.6 kV to three-phase supply. This is the distributed network. From here, we will actually have different kinds of loads. Like here we have three-phase, right? RYBN. We will just pull like RN. This will go to a home H1, and another single phase will go to home 2, and another will go to home 3. Let's say this is kind of distribution network we have, and let's say, for example, I'm just taking, let's say I'm here connected, here I have connected a 220 volts, like uh, 150 kVA transformer, and like some even by V2, and this transformer is serving the distribution purpose. Now these homes won't remain same. Like as the time pass by, and like let's say now, from now, after 3 years, my houses will be more in that area. Like every day we are seeing many more constructions are happening, just they're building many more apartments, and in that case my load demand at the distribution side will obviously will increase, like it will actually double like in the period of 5 to 6 years. There is no wonder in that. So in that case, let's say at this point of condition, my 150 kVA transformer is okay to support the load at the households. Like my house and the 2 3 houses nearby me, we are happy with 150 kVA. But when my households is just increasing gradually, every house 5, house 6, house 7. Now let's say I don't, sorry, now let's say I'm not to support this entire household, 150 kVA is not at all possible. Now I might require 500 kVA transformers, like because I already said that kVA is analogous synonymous to current. Now my my entire household needs a bigger transformer. Let's say I need when I say I, it is my entire household, this entire distribution household. This area requires 300 kVA. Now I can change my transformer to I can change, but that's not a viable option. Now how can I increase my transformer rating? Either one option is we have to remove that 150 kVA and we will buy another same voltage rating kVA which is of 300 kVA, which that means my voltage is same because I am connecting all 440 volt supply and taking to every household. That's fine, but my current load is increased now. Now I have to increase my kVA rating of the transformer. The one of the option is I will disconnect my 150 kVA transformer and I will connect the 300 kVA. I will buy another 300 kVA transformer from the market and I will connect. I will replace it with. But what is the disadvantage in that condition? The first condition is I am replacing a healthy transformer, but because my healthy transformer, which is a 150 kVA, that is serving the purpose. Now I am replacing it, even if it is not damaged. So that I am not using my healthy transformer. And second thing, I am buying a higher kVA rating transformer, which will be much more costly than my 150 kVA transformer. Not only I am increasing my investment, but also I am keeping my healthy transformer aside. That is of no use now. So that should not be the viable solution for that. So what should be a viable solution is now I will buy a exact transformer with the same voltage ratings and same kVA and I will connect in parallel with the existing transformer. Now 150 kVA, I am connecting another 150 kVA. Now my transformer network can able to supply the load. So yeah, that is the first most important advantage of a parallel operation, the application of a parallel operation of transformers. So one of our attendees said that load sharing. Load sharing is very important. So that in that case, parallel operation plays a very big role. And yeah, so that was the first condition. And yeah, obviously when I buy a 150 kVA transformer instead of 300 kVA transformer, my investment is I have saved half of the money. Like I have saved it, and in turn I am already using my existing healthy transformer of which is of 150 kVA. Yeah. Now yeah, there are even more advantages of other advantages of parallel connection of transformers is like let's say I have connected two parallel transformers operation like they are operating. Let's say one of the transformer got faulty, like I have connected, let's say, two transformers uh, and these two are operating in parallel. So when these two are operating and these are supplying a load here, load, let's say 150 kVA and my load is, let's say, 200 kVA and this is 150 kVA. Now these two can easily supply my 200 kVA load. Now let's say one of my transformer is went fault, it got damaged and I need to repair it. Now what can I do? I can disconnect this transformer. I can I can take it to repair this transformer, and meanwhile while it gets repaired, this 150 kVA transformer can supply to 200 kVA transformer, but it may not be 100% sufficient for my load, but at least out of 10 houses I can supply to 8 of my houses without any problem in power interruption for these 8 houses. Maybe I can change sometimes to 8 houses, sometimes to last 5 houses. Like that I can manage. At least I am not cutting the entire supply. Now when there is no parallel operation, let's say I am supplying only, I'm supplying to my entire load with only one transformer. There is no parallel operation. Sorry. Yeah, let's say I'm supplying my entire load with only one transformer. If at all, if if at all this goes faulty, so sorry, yeah, if at all this goes faulty, then my entire power will be gone. There is no supply to even one household, so there will be a power interruption, and it will be there till I get my transformer repair. So that's the advantage of parallel operation of transformers. I can even if one goes faulty, I can maintain my load. Like, and I can still give supply to my load. Another one advantage is, let's say my two transformers are supplying the load. I have one exact transformer as a I kept one transformer as a backup. So when I kept a transformer as a backup, and even now I don't have to worry about any interruption in any household, because once it goes to repair, what I will do, I will just connect this backup transformer in place of the faulty, and I will send this to repair. Now there is no power interruption. There is no 100. Now I am serving my load 100%. Even one house is not experiencing any power outage. So that are another advantages of parallel operation apart from the load sharing. So yeah, those are the advantages of parallel operation of transformers. Now let's look at systems. Okay, okay, yeah, I will write here. So let's get back to our conditions to satisfy parallel operation. First one we already wrote there. My I'm again writing it here. Voltage ratings must be same. Yeah, and yeah, second condition is, we just saw kVA ratings might be different, because kVA is synonymous to current, right? Even if I connect two different transformers with different kVA ratings, they have their own rated currents. Any current might flow to the windings, but kVA ratings might be different. But we have to make sure that the LV and HV side rated currents are satisfied. We shouldn't overload the transformer windings. So kVA ratings may be different, but LV windings and HV windings current ratings must not be exceeded. We should not this particular condition says that we should not overload our transformer windings. Yeah, we can connect any kVA transformers in parallel, but we should make sure that the current ratings are not being exceeded. Now the third condition and very important condition is polarities. Polarity must be same while connecting two transformers in parallel. Now this is not only an important condition, but if we don't follow this condition, it will actually damage it. There is a chance that we are damaging a transformer, and there might be there might be a plausible situation for a short circuit. We will just see quickly how that happens. I will just draw it here. Let's say I have two transformers, and yeah, so this one is transformer A, this is transformer B, this is transformer A primary, and this is transformer A secondary, and this is transformer B primary, and this is transformer B secondary. Now let's say this is my dot convention. current entering one side, current leaving one side. Now let's say I have my transformer is same transformer. Let's say I take this transformer 400 volts by 200 volts. Now when I apply both transformers with 400 volts, and how much it will appear here, 200 volts, because I'm giving rated supply at the primary winding. Now if you see, if these two are dots, let's say this is dot is plus, now how much voltage I'm seeing here, 200 volts, because they both are in parallel, not in series. So when I mistake that to, now without checking my polarity, let's say I have connected the dot polarity here and I have now connected in parallel. Now this is plus and this is minus and this is again 200 volts, but with a reverse polarity. Now if we see, the total voltage is very high. Now my load is seeing 400 volts, and this is nothing but a short circuit condition. The voltage will be very much high if it is with the transformer different readings. Now when we are connecting these two transformers in parallel, we are actually approaching the short circuit condition. So this is a very important condition we have to make sure before connecting any two transformers in parallel. So again, I'm just, polarity should match, and then only we should connect a load, or else a very high current will flow, because we're giving we're practically short circuiting it. Yeah, so these are the conditions which we have to make sure and ensure before connecting any two transformers in a parallel. Now let's draw an equivalent circuit when we connect two transformers in a parallel condition. So yeah, equivalent circuit of two transformers connected in parallel. I am referring the both equivalent circuits to the load side. We will see why we have referred to load side. So yeah, let's say I'm just drawing the induced voltages. I'm not drawing the supply voltages. Let's say in my primary side, it is the primary side induced voltage E1, and this is primary side induced voltage. Now when I have excited my primary with the supply rated voltage, and E1 is the voltage induced in my primary, then E2 will be the voltage which will be induced in the secondary. Okay, now this is E2, this is voltage. Now yeah, we have resistance and impedance in the primary side. Since we are referring it to the load side, I have converted I have shifted all the resistances and impedance to the secondary side. This is the entire equivalent secondary resistance, let's say. Yeah, this is entire this is all the impedances referred to the load side. So this is how my equivalent circuit looks like, but I have connected two transformers in parallel. So let's see equivalent circuit of my load side. What we have in the load side? We have two windings which will have two induced voltages. Let's say I'm calling them as EA and EB. EA, which is the induced voltage in my first transformer of the secondary side. Now it will have its own resistance and impedance, and we call it as REA, JXEA. Now I have another voltage source which is in parallel with my EA, and it will have its own resistance and impedance. I will call it REB, JXEB, and the induced voltage I am calling it as EB. Now these two are in parallel. Now here I am connecting my load. So yeah, whatever current I am getting at my load is because of these two voltage sources only. Let's say this is load, and yeah, and some current will flow through here. The sum of these two current will flow through the load. Now, so yeah, if you apply 400 volts in the primary, and I will be getting 200 volts in the low voltage side, and the same 200 volts, which is EA, will be 200 volts, and my EB will also be 200 volts. Now, this is an ideal condition, but in practical condition, what happens whenever I apply my primary voltage, the voltage which induced in the secondary voltage in two different parallel transformers might not be same. There might be some variation in the secondary voltages. Let's say it is supposed to be 200 volts, right? Let's say I have connected a switch here. I have not connected any load here, but if you see, whenever my switch is open, it means that no load condition. I have not connected any load. Now, if you see, if these two are supposed to be 200 volts, that's what same voltage ratings. So someone has joined. 1 second. Now, whenever these two voltages are not matching, there is a potential difference between these two volts. What happens when there are two parallel branches with different voltages? What will happen? A circulating current will flow in that loop. So here, this is the loop, right? So in this loop, a circulating current will start to flow from high potential to low potential. So whatever potential is high, EA or EB, whatever mismatch we are observing in practical conditions, the current starts to flow, which we call as no load current or circulating current, from high potential to low potential. So that's the that's the condition which we don't desire, because we expect those two voltages to be same in magnitude. But when this kind of mismatch happens, a no load current will flow among them, which we call as a circulating current. Yeah, so that's what happened when any voltage mismatch happens. Now, if you see, whenever we close this switch, we operate our transformer in, let's say, full load, because that's what the purpose of connecting any two transformers in parallel. We want to operate our transformers with its full potential. Now, the total current which is flowing through the load, let's say this is secondary side, I name it as I2, and the I2 is responsible, like IA and IB are the two currents which are responsible for I2. Now, the summation of this IA and IB will be contributed to I2. But what is the amount of current like that should be supplied by EA, and what should be the current supplied by EB? What should be the values of IA and IB? Who decides what should be the magnitude of IA and IB? So what is deciding factor is here the impedances. Now, with a simple circuit analysis and network theory principles, it's just a simple nodal analysis or any mesh analysis. We can just implement those rules, and we can actually find the values of IA and IB. And from them, we can also find, let's say we know the load voltage, load current I2, and we can, using some simple nodal and mesh analysis, we can also find the values of IA and IB. That's a simple network theory like application we can use. Now, with this theory, with this knowledge of this parallel operation, and how we connect to two transformers in parallel operations, and with this theory, we will move forward a bit, and we will solve a couple of numerical problems which will be useful for you to solve your assignment as well. Now, I want you also to pick up your pen and papers, and keep your calculators aside. Let me also bring my calculator out. And yeah, please pick up a pen and paper and try to solve this problem with me, which will be useful for you to solve your assignment questions as well. And yeah, so let's look at the given data first. So we were given a two single phase transformers. Okay, those two single phase transformers are in parallel. Okay, we are discussing the parallel operation of transformers. So transformer 1, okay, you can observe here as well, the two transformers are of different kVA ratings. 200 kVA is transformer 1, and my second transformer is of 300 kVA. It could be different. We don't actually that doesn't bother us, because kVA means each winding will allow different currents to flow through them. That's okay. As far as my voltage is same, so you can see here the HV side of transformer is same, that is 11 kilovolt bus. So it was given that my HV sides are parallelly fed from a 11 kV bus. So fine. But the secondary side, you see 230 volts is one transformer and 240 volts is another transformer. There is clearly a 10 volts difference in that. So whenever I try to connect these two transformers in parallel, the voltage ratings are different. Then obviously my secondary in my secondary LV side, circulating currents will definitely flow, because there is a 10 volts of voltage mismatch. So yeah, that's what our primary observation from the data given. Now let's see what additional data we were provided with. And we were given an equivalent impedance as well for each transformer, but in terms of percentage. Okay, he has given the data. Let's say my transformer 1 is having the ZE, which is of that percent. We will ultimately convert that percentage value of impedance into actual ohms in terms of actual SI units. That we will see. We will just have to multiply with that voltage and divide it by current in that HV side or LV side, whichever side we are performing the calculations, and we will get a actual SI units of that impedance. That's not an issue. And what was the question asked? Let's get into the question first. Estimate the no load circulating current. Obviously there will be a no load circulating current in the LV side, because there is a voltage mismatch. Okay, now we have to calculate the no load circulating current. Yeah, so I don't think this is a very difficult question to start with, because we were given everything. We were given the impedance of the transformer, that is referred to the any side, whichever side we want to perform. So no load current, they were asking about no load current, so obviously it will flow in the secondary side, which is LV side. And yeah, so let's start solving this. And yeah, let's first convert this impedances into ohms, because that's not we are going to move forward with. First let's convert this impedances, which in terms of percentages, into my ohms. Let's say, so what was the side we are trying to calculate? This is no load circulating current, which will be obviously on the LV side. Now LV side, my Z1 will be, so I was given, what was the percentage impedance of transformer 1? J 4.75, that is percentage multiplied by, I need to multiply with actual ohms, that is LV side voltage divided by LV side current. What is LV side voltage? 230 divided by current. How can I get the LV side current? Anyone tell me how to get LV side current? Is equals to
KVA divided by primary voltage. Secondary voltage.
Primary means the first transformer secondary voltage. Yeah, that's correct. So what is the KVA? 200 into 10 cube KVA divided by, what is the voltage? 230. So yeah, we have to substitute this here and multiply this with my given percentage of impedance, and we will get the impedance. So can someone please calculate that? I'm also calculating. One plus 4.75 I divided by 100 multiplied by 230 divided by 200 kVA multiplied by 230. Okay. I'm writing it both in conjugate form as well as a complex form as well as polar form. So first I'm writing A plus IB form, 0.00264 plus J 0.0125. So yeah, if anyone calculated with me, just tally with it. If you are getting different, please tell me. And I am also writing it in polar form, that is r theta form, which is 0.0128 at an angle of 78.11 degrees. Yeah. So this is what Z1 I got. I'm just take a line. Now let's calculate Z2 as well. Again, Z2 is a secondary transformer's actual impedance referred to the LV side. Now, what is the percentage? 1.75 plus J5 divided by 100 multiplied by, what is the secondary voltage for the second transformer? That is 240 divided by kVA of secondary transformer is 300. 300 into 10 cube divided by 10 cube divided by 240. Yeah, someone please calculate with me this one. 1.75 plus 5i divided by 100 into 240 square 300 into 10 cube. So I'm writing again a plus ib form, as well as people who are calculating, just please tally with my answer. 0.00336 plus 0.0096i. Okay. Now my polar form for the same will be 0.010 at an angle 70.79. These units are in ohms. So that's the whole purpose why we are doing this. We have to convert that percentage into ohms. Now we have both impedances of the secondary side of my LV side of my transformer, which are two parallel transformers. Now I have my impedances. Now I have my voltages. It's a very simple thing. Since they already said that it's a no load condition, let me just draw a simple circuit. It will be much more easier to visualize like what exactly we are trying to calculate. I'm just drawing the equivalent circuit of my secondary side. Okay. Yeah, these two are in parallel, and they said that there is no load. The switch is open. So this is Z1, this is Z2 we calculated, and this is E1, and this is E2. Don't confuse E1 and E2 with primary and secondary, but this is just two different transformers in my secondary side. Now, yeah, we know E1, which is how much is E1? That is 230, and E2 we know 240, and we know Z1 and Z2. Now we were asked to calculate the current which is flowing inside this loop. Can anyone tell me what is this no load current formula? It's a simple network problems. Like if you assume this is the current direction, like the same current will flow here. If you assume this direction, we will get another current. But ultimately, current will flow from high potential to low potential. Now here current will flow from 240 volt source to 230 volt side source. Now, yeah, 240 minus 230, difference of the voltage divided by the entire impedance, that is Z1 plus Z2. Now, can someone tell me, Z1 is already here and Z2 is already here. Now someone calculate and tell me the answer. I'll just okay. I'm just writing the magnitude and angle. I'm writing the polar form here. That's what I got. 436.68 at an angle of minus 74.810. It is degrees, and this will be in amps. Don't worry if you take 230 minus 240. Anything it will be same. If you take 230 minus 240, the answer will be negative, because that's a convention, right? that will get. Now because I took 240 minus 230, that's the actual direction of current flow. I got the positive answer. So yeah, you can take any notation. So yeah, that's the first problem. We have to just calculate the no load current flowing. Now we were asked to estimate, what is the question? Estimate the ohmic losses in watts caused by the no load current. Now we already calculated no load current. We know the value of the current, and we have to calculate the ohmic losses, that is resistive losses. Now, which part will contribute to my ohmic losses? The real part in my like whatever, like I have a total impedance which is A plus IB form, R plus JX form. My real part, which is a resistive part, will contribute to my ohmic losses. Now how do I calculate my ohmic losses at no load? Now I know my no load current, that is I square no load losses are I square R losses. Then the R will be the total resistive part in my impedance. No load ohmic loss is equals to INL magnitude of my no load current square multiplied by R. Let's say this is R total. So what is my no load current magnitude? That is 436.68 square. Now my R which is the real part of these two. Now this is the real part in first impedance, and this is the real part in second impedance. 0.00264 00336. Okay, please someone calculate this for me. 436.68 square multiplied by 0.00264 plus 0.00236. Yeah, I got 1144. Okay, I mean 1.144 kilowatts. So that's the ohmic losses I got. It's yeah. Once we know the no load current, which is circulating current flowing between these two voltage sources, we can directly calculate I square R loss. I know the no load current. I know the total resistive components in the entire circuit, closed loop. So that's how it's simple. Now let's see the last question for today. This is, we have to estimate the no load LV side terminal voltage. Again, there is no load. I will just quickly draw circuit here. This is E1, this is Z1, this is E2. These two are in parallel, and okay, I have connected a switch here for my load. Sorry, this is my load and this is switch, and I have not closed the switch because it's a no load condition. And yeah, this is I1, this is I2. In this case, when there is no load, I2 will obviously equal to minus I1. That's given that because just now we saw that in the no load condition. Now we were asked to find V2. Okay, it's now very simple because there is no load in the output side. There is no load current. Now V2 is nothing but E1 plus I1 Z1, which is also equal to, sorry, E1 minus I1 Z1 or E2 minus I2 Z2. Simple. So what would be the no load side LV terminal? Now what is E1? 230 minus I1. I1 is nothing but our no load current. How much is the no load current? 436 at an angle of minus 74.8. Okay, I have calculated this with respect to 240 minus I1, right? So this will be I2. Yeah. So yeah, this will be minus because that 436 is a positive if we see from 240 side, but we are calculating from I1, this minus into Z1. How much is Z1? 0.0128, 78.11. Okay, so please calculate this, and we can also tally this answer from the other expression, which is E2 minus I2 Z2. That can also be done. Okay, maybe someone of you can try the second one, which I'm trying the first one, and then we will see whether we both are getting the same answer. So let me just calculate this one first. 436.68 at an angle of minus 74.8 multiplied by 0.028 at an angle of 78.11 is to 30. Okay. Sorry. Okay. Now what I got is, I'll be writing here. I'm writing it in a polar form. .207 at an angle of 0.16, and yeah, you people also tally it from the other side, that is 240 . Okay, yeah, 240 minus 46.68 minus 74.8 multiplied by Z2. How much is Z2? 0.010 angle 70.79. Yeah. Let me also do this. Two 35.644 at an angle 0.074. So I'm getting a difference of how much? Around 7 volts I'm getting. I think there somewhere I have taken less decimals or some angle difference I'm getting, but it's fine. So yeah, 235.644 seems more like a better answer because somewhere I missed some angles. Yeah, you can tally it from your side as well. So that's how you calculate when you know the no load current and also all the impedance values and all the induced voltages in the secondary side. That's how you can calculate the terminal voltage. Terminal voltage is nothing but the induced voltage minus the drop across the impedance part. So yeah, we will just have a look at the problem which we solved. So we were given a transformer 1 and 2 with different ratings and same voltage ratings with a slight mismatch in the secondary LV side voltage, which aids for the cause of these circulating currents. And then we were asked to find the no load circulating current when these two are connected in parallel. So for that, we just found the impedances in SI units first, and then we applied simple circuit analysis concept of finding circulating current between any two nodes, and we got a circulating current, and then with that circulating current we estimated the ohmic losses by I square R formula by taking the real part of the impedances, and then we calculated the terminal voltage, which is nothing but the induced voltage minus the drop. So yeah, And prior to solving the numerical problem, we saw the concept of parallel operation of transformers, and what are the conditions to be satisfied, and what are the precautions we have to take before connecting two transformers in parallel. We saw those, and those conditions we have listed out, and we have seen the equivalent circuit of any two transformers connected in parallel, and how the voltage distribution will happen, and how the current distribution will happen, and what values does our current values depend. It depends on the impedance values as we discussed. So we saw those conditions as well, and then we started solving our problem. So yeah, so if you have any doubts regarding the topics discussed today, please ask me. And if you have any doubts on other topics as well, please ask, and we will try to get back to you on the set questions. And you can also raise questions in our discussion forum as well. And please join the session which is going to happen by 7 p.m. today. And in that, you will be discussing the concepts of two-phase to three-phase connections, two-phase to six-phase connections, and some more concepts on that. And one of my co-TA will discuss those with you. And yeah, I request everyone to attend the 7 p.m. session as well. So yeah, are there any questions in the topics discussed today? Please do let me know. So yeah, if there are no more questions in today's session, we can end our session now. And yeah, we look forward to meeting next week. Thank you for your time. Thank you for listening patiently, and we will meet next week. Thank you.